Hi guys, welcome back to my channel. Today I want to talk about PV diagram. Before we dive into the 4 different PV diagrams, I want to first of all talk about first law of thermodynamics, okay? As you can see, this equation here, delta U equals Q plus W. So this is the formula for first law of thermodynamics, saying that energy cannot be created nor destroyed, but it can be transformed, right, from one form to another form. And then in this case, this delta U, or sometimes you see delta E, this depicts the internal energy of a system, okay? So this example I gave you is this gas container containing gas molecules, and this is my system. And everything surrounds it is the surrounding of the system, right? Okay, so the internal energy of the system are affected by 2 factors, as you can see here. One is Q, one is W. And then Q is heat energy. And then this is very intuitive. If I add heat, I put this thing on a stove, I heat it up, right? Then I gain heat energy, right? So my Q is a positive Q, means I gain heat energy from the heat from the stove, right? On the other hand, if I I remove the heat from the system, let's say if I remove this thing, I put it in the fridge, then the heat will flow from the system to the environment in the fridge, right? Then my delta Q, or my Q in this case, will be negative because I lose heat, okay? All right, so what about W? W is really work, okay? Thermodynamic work. So how does this work, okay? So basically, you see the gas molecules in this container, if they move more violently, if they, let's imagine they're dancing and moving and jumping, they were trying to touch the interface, they're trying to touch the piston, then we say these gas molecules, they're doing work, okay? So the system or gas doing work, okay? All right, so when they do work, when they're dancing so violently, of course, they expand the volume, right? This volume, V, would increase, okay? So on MCAT, when you see the volume of the system increase, then you know, oh, the system did some work, okay? And then because the system did some work, we can intuitively also think that, oh, the system must lose some energy, okay? So in this case, W, the thermodynamic energy, is lost in some way, so it's a negative sign, okay? Whereas on the other hand, if you see the picture on the left, here, it's the surrounding, it's my hand that's doing work on the system, on the gas. I press it down, and then I compress the volume, right? So in this case, my volume really goes down, and it's the surrounding. My hand is part of the surrounding, right? It's the surrounding that doing the work, okay? That compresses my volume. So in this case, the system kind of gained some energy from the work that the surrounding did, right? So it will be a positive W, okay? All right, so some students are really confused if the W should be positive or negative. How do I do the calculation? It really doesn't matter. It only matters if the surrounding is doing work on the system or the system is doing the work on the surrounding, right? The positive really means the system gaining the energy, right? Gaining the contribution that the work did by the surrounding, right? So it's a plus W, okay? Whereas the other flip of the coin, the other side of coin is the negative W, meaning that the system did a lot of dancing and moving, so that it kind of loses some energy, right? Because W is one factor of this delta U, which is the internal energy of the system, okay? I hope that makes sense. So on MCAT, one more thing I want to say, that if you see the equation that's given is delta U equals Q minus W, that is okay. It doesn't matter what the original equation looked like. It's okay. You just assign the plus and negative sign according to the rationale we just discussed, okay? All right, now let's move on to the PV diagrams, okay? So the PV diagrams, the first one is the isobaric, okay? So before we jump into the nitty-gritties, I want to point out an equation that is W equals P, I should say delta P times delta V, okay? So that's why the PV diagram is important, because the change of P and the change of V can tell us the change of work, right? And then work is part of the component of the internal energy of my system. So I'm interested in knowing how is the work getting done, so that I can infer how does the internal energy of the system change, right? Okay, so here, isobaric is really constant pressure, because baric means pressure and iso is the same, right? Constant pressure. Okay, so let's say my pressure can only be 10, okay? So I'm going to draw a horizontal line here, okay? So I can't do 15, I can't do 5, it's only 10, it's constant, okay? So constant pressure at 10 Pascal, let's say. Okay, so my system changes the volume from V1 to V2, okay? So from here, V1 to V2, okay? So really the change of the volume here, going from V1, V2, really expanded volume, right? Expanded, because V2 is larger than V1. So expanded my volume. And then the P is constant. Let's say V1 started from 10 meter cubed to 15 meter cubed. So how much work is done is basically the area under the curve, right? That's the most important thing you want to get out of isobaric diagram, okay? So in this case, delta W is 10 times delta V is 5, right? 15 minus 10. And then that gives me 50 joule, okay? All right, so the $1 million question here is, this 50 joule of differences for work is done by whom? By the surrounding or by the system, okay? And then as you can see, my volume really expanded, right? That's just like the case here, this red scenario where the volume expanded. So it's really the system or the gas that's doing the work, right? So this delta W is not the work done by the surrounding, but it is the work done by the system. In other words, the system kind of lose some internal energy, because W is the component of the internal energy, right? And now I'm not contributing delta W to my internal energy, delta U, but instead I'm subtracting it, right? So from this PV diagram, I calculate how much work the system did. And then if I were to calculate delta U, this 50 joule must be has a negative sign before it, okay? All right. So this is everything you need to know about isobaric diagram, okay? Now let's move on to isometric, okay? So isometric, the metric here, or isochoric, means constant volume, okay? Constant volume. So if the volume was constant, let's say here, my volume can only be 10 meter cubed, okay? I'm not moving to 5, not 15. It can only be 10. Then it doesn't matter how my pressure goes up or down. My work will always be 0, right? Because work equals P times delta V. And my delta V is 0. My V is 10, but my delta V is 0. So my delta work will always be 0, okay? Nobody did any work, okay? So in this case, since my delta W is 0, so my delta U only relies on Q, right? Delta U equals Q plus W or minus W, whatever. Then this W is 0, so it only relies on Q, okay? All right, so I think that's everything you need to know about isometric, okay? Constant volume. And then also you can see that there's really no area under this graph. So which means what? No work is done. No work by the system is done, right? No work is done by the system. Okay. Okay, now let's move on to isothermal, okay? Isothermal, I have more to talk about, okay? So first, isothermal, thermal means what? Temperature, okay? Temperature. And then here, isothermal means it's constant temperature, okay? So first thing you need to know is temperature is constant. Okay, so temperature is constant meaning what? Constant is temperature really tells me my delta U is constant, okay? Because temperature is the quantified number that you use to measure if delta U it changed or not, okay? After the two components Q and W, after they both differently affect delta U, then how do we quantify in a quantitative way to know for sure that, oh, delta U did change? It's the difference of temperature that tells us that, okay? So here, the temperature is constant, so that we know that the delta U that is proportional, directly related to temperature would also be constant, okay? So temperature constant tells me delta U is constant, okay? So this tells me delta U equals 0, okay? So if delta equals 0, then delta U equals Q plus W, then Q must be negative W, or W equals negative 2. Then my delta U can be 0. Right? Meaning delta U is constant, aka temperature is constant, okay? Okay, so this conceptually, you know that, okay, negative W is the work done by the system. So it means like as soon as some kind of work is done by the system, that I have to quickly spontaneously add some heat energy into the system, right? Or the other case here, which means negative Q is removing heat. As soon as the heat is removed from the system, the surrounding has to very quickly, spontaneously do some work on the system, okay? All right, so that's the conceptual understanding of this. All right, so what does the graph look like though, okay? The isothermal graph, what does it look like, okay? So let me remind you the ideal gas law equation, PV equals nRT or NKT in some cases, right? It's the same thing, okay? It's a constant. All right, so here we can see that P equals, if I arrange it, equals nRT over V, right? Okay, so here you can see that the T is basically constant because we set temperature constant, right? And then R is a constant, right? And then the number of moles is constant as well. I'm not changing how many gas molecules I have. So this denominator is basically constant thing, right? So the graph of this PV diagram is basically kind of look like P equals 1 over V, okay? So it's a hyperbola graph that looks like this, okay? And then it makes sense, as you see, as I go from V1 to V2, as I expand my volume, really my pressure is decreased from P2 to P1. Okay, that makes sense. As my volume increases, the pressure decreases because volume expands. Then for the gas molecules, for them to travel from one side to the other side, it's just harder for them to jump the larger distance, right? So that the force, the force on the surface of the container, pressure is just force over area, really decreases, okay? All right, so this is the isothermal diagram, okay? And then the other thing I want to point out is that this isothermal diagram is called an, let me clean this up a little bit. It's really called an isotherm. This line is called an isotherm, okay? Meaning what? Meaning every single point here, I got P something, okay? This is P, let's say this is a P2, this is V1, okay? So, and then let me grab another point where I have P1 and V2, okay? So this point and then this point, they really have the same temperature, okay? They have the same temperature, meaning that P2 times V1 equal to P1 times V2, right? Because this is proportional to temperature. This proportional to temperature, right? And then temperature T this is T something, let's say T null, right? They're the same temperature. So every single temperature, every single spot on this isotherm gives us the same temperature, okay? And then you might say, oh, why P2 PV is directly proportional to T? Because also you can derive from this equation that we know that N is constant, R is constant. So PV equals T, so PV is really directly related to T, okay? All right, so this is the isotherm. So now, what about I draw another isotherm, okay? So the other isotherm will give me a different temperature, T2, okay? And then this is T1, okay? And then also the same thing, on the other isotherm, every single point, let's say this point, or this point, okay? I always have the same temperature, T2, okay? I guess I should say this is T null. Okay, all right. So the question is T null smaller than T2 or it's larger than T2, okay? So the answer is T null is smaller than T2, okay? T2 is larger than T null, okay? Why? Because the P and PV of the black isotherm is smaller than the PV, P times V of the blue isotherm, okay? So that T2 is larger than T null, given the relation that PV is directly related to T, okay? All right, so this is isothermal diagram, okay? So lastly, let's move on to adiabatic, all right? So adiabatic is the process where you have no heat exchange, okay? So if you have no heat exchange, okay, meaning what? Meaning your delta U equals Q plus W, but this part is not accounted. So delta U is only relying on work, okay? All right, and then this adiabatic process is basically work that is done really quickly, okay? It's done quickly enough without giving it enough time to exchange the heat, right? Because if there was enough time, if you do the work really slowly, then the heat will just always flow from the warmer environment to the colder environment, given the second law of thermodynamics, right? But if you like press the piston really quickly, and then you did the work, but you really didn't give the system enough time to exchange heat with the surrounding so that we can keep this heat constant, okay? There's no heat exchange. Or we can just put the whole apparatus in the isolated system, insulated, and then we can also make this no heat exchange effect, okay? All right, so this is actually the opposite of this isothermal process, right? Because the isothermal process, we want to do the work as slowly as we can so that we can compensate the loss or adding of the heat, okay? All right, so adiabatic. Okay, so what does the graph look like? So the graph also looks like, kind of look like the isothermal. It's a hyperbolic. As V1 goes to V2, P2 decreases, right? All right, P decreases from P2 to P1. But the thing is, it would decrease in the more dramatic way, okay? So this graph, this hyperbolic is really deeper than the other isothermal one, okay? And then why is that? Because we said the isothermal scenario is when the temperature is constant, okay? But here, the temperature is not constant, okay? Since the work is being done, and then when the work is being done, no heat exchange is compensating this process, so that I do have a drop of temperature, okay, from T2 to T1 as I do the work. That's why this graph is steeper than the isothermal one, okay? All right, so that's all four graphs, okay? So if you want to draw it, you really want to do some practice of, let's say, drawing all four graphs in one PV diagram and recognize which one is which, right? And then also I want to show you this graph. This graph really summarizes everything I discussed today. This is when I first learned PV diagram, I came up with this summary, okay? As you can tell, I'm a fan of table graph, okay? Yeah, you can do the practice of just hide some of the content and then just try to come up your understanding and see if you really understand all four types of PV diagram. All right, I hope that's helpful.